All right, let's get right into it because this is a big one. We're talking about a really exciting discovery in quantum computing. Researchers have just added a brand new, powerful tool to the quantum algorithm playbook. It's called the Quantum Hermite Transform. And, it just might open up a whole new class of problems for quantum computers to solve. So, think about it for a second. What really makes a quantum computer powerful? It's not just the qubits, right? It's the fundamental algorithms it can run, its primitives. This is its core toolkit. But what if that toolkit was actually pretty small, limiting what you could even try to build? So here's our game plan for this explainer. First, we're going to dig into why quantum computing has this toolkit problem. Then we'll meet the new tool that might just solve it, the QHT. We'll peek under the hood at the really clever engine that makes it all work, see what it can actually do, and then we'll look ahead at what this all means for the future of quantum. Okay, first things first, the quantum toolkit problem. We really have to get the why before we can appreciate the what. So why is the hunt for new quantum primitives so important right now? Well, here's the thing. For all the hype around quantum computing, most of the big-name algorithms we talk about are built from just a handful of core ideas, like the quantum Fourier Transform. And that scarcity, well, it's a real bottleneck. It really restricts the kinds of problems where quantum computers can actually show off and give us a real speed up. So if we want to break through that bottleneck, we need a new tool. And that brings us to the hero of our story today, the Quantum Hermite Transform, or QHT for short. And believe me, this isn't just some small tweak. It's like adding a completely new kind of instrument to the quantum workshop. So what exactly is it? The Quantum Hermite Transform, the QHT, is a brand new primitive that you can kind of think of as the Gaussian cousin to the very famous Fourier Transform. So if you're ever dealing with problems that involve Gaussian distributions, bell curves, which are literally everywhere in physics and stats and signal processing, this is the tool you've been waiting for. Let's put this side by side to really get it. The Quantum Fourier Transform, the QFT, is an absolute pillar of quantum computing. It's the engine behind huge algorithms like Shor's. The QHT is designed to be just as fundamental, but for a totally different class of problems. It lets us switch our perspective to see a problem in the language of Hermite states. You can think of these as the natural states for systems that act kind of like a pendulum or a vibrating string, basically systems described by the Quantum Harmonic Oscillator. Now you might be wondering, if a tool like this is so useful, why are we just hearing about it now? Well, the answer is this absolutely brilliant trick that's under the hood, a fast-forwarding engine that makes the whole thing run. Okay, here's the secret sauce. The entire algorithm is built on a totally revolutionary way to simulate the Quantum Harmonic Oscillator, or QHO. And the QHO is one of the most fundamental models in all of quantum mechanics. It describes everything from atoms in a field to how molecules vibrate. It's a huge deal. What the researchers did was they found this incredible mathematical shortcut, a recipe, let's call it, for how the QHO evolves over time. And this recipe is so efficient, it's like having a fast-forward button for the simulation. Seriously, imagine you want to know what happens on the 1000th page of a book. Instead of reading all 999 pages before it, you could just jump straight there. That's the difference. This jump is what we call logarithmic time, and it means an exponential speedup. It just blows past the normal speed limits of simulation. And this fast-forwarding isn't just a cool party trick, it's the engine that powers the whole operation. It lets them do something called quantum phase estimation with incredible accuracy. You can think of this like using a super precise tuner to find the exact frequency or energy of a quantum state. And by doing this so efficiently, they can perfectly build and check the Hermite states they need for the transform. So how do they actually do it? How do they build one of these perfect states? What I love is that these next couple of images come straight out of the research paper. So we're seeing exactly how they did it. Step 1, you start with a good enough guess. They use this known mathematical function that's a pretty close approximation of the real thing. It's not perfect, but hey, it's a solid, easy-to-create starting point. Then comes step 2. They take that rough guess and they refine it using this really clever technique called a fixed-point quantum search. Imagine you have a fuzzy, static-filled radio signal. This search is like a filter that just zeroes in on the right frequency, boosting it and tuning out all that noise. And of course, it's powered by that fast-forwarding engine, letting them find and amplify the correct piece of their quantum state at incredible speed. And what you get at the end is a near-perfect Hermite state. After that whole filtering process, they're left with the exact quantum state they were looking for. This right here is the fundamental building block for the entire Quantum Hermite Transform. Now, of course, like any tool, it has its sweet spot. The researchers show that this fast-forwarding trick is most effective in what they call the low-energy zone, which you see here in blue. In this zone, the simulation is just incredibly accurate. It still works pretty well in the medium-energy green zone, but the approximation starts to break down when you get to the high-energy orange zone. The key thing to remember, though, is that for a lot of important problems, you only need to work in that super accurate blue zone anyway. Okay, so now we get to the really fun part. We have this new super efficient tool. What can we actually build with it? What does quantum advantage look like in action here? Well, the QHT seems to unlock a whole set of new quantum superpowers. For one, it lets us efficiently test properties of functions that use Gaussian distributions, those bell curves, which was really hard before. It can help a quantum computer learn complex geometric ideas and even simulate other quantum systems more efficiently. And just to prove its power, the researchers showed it could solve a version of a famous computational learning problem, demonstrating a clear quantum advantage where classical computers would just get stuck. And that brings us to the big question. What's next? You know, the authors of this paper, they don't see the QHT as the finish line. They see it as a new beginning, as an open invitation to the entire quantum community. And I just want to end with their own words because I think it's so powerful. They write, "We invite others to use this as a building block for new quantum algorithms achieving exponential advantage." So this isn't just one new algorithm, it's a new foundational tool. The question they're leaving us with is a really exciting one. Now that this tool is out there, what new worlds of computation are we going to build with it?